So thanks for the invitation to present our work, which we are doing together with Paul Thiessen from NIH and Emma Szymanski from the University of Luxembourg. And currently, we have published this Mulgeny organic chemistry ontology, MOCO. It's organic chemistry only. There's also an inorganic one, which is not published yet. It currently contains about 93,000 chemical classes. And we did classify about 21 million compounds. And what you see here is the upper level. So we have calculated properties. So for example, drug-like compounds, hydrophilic compounds, things like that, which are of importance for medicinal chemistry. We have criteria or classes which pertain to the compound as a whole. So therefore, the upper level is compounds. And we have substructural concepts like scaffolds or something like that. So these are the upper levels of this ontology. And basically, this is available or published on the PubChem's classification browser. So there you can see the Mulgeny organic chemistry ontology. And basically, everybody can use that ontology. In this ontology, we have about 4.7 million compounds classified. And here you see a little bit the compound classes which have been, or compound collections which have been classified. So for example, the Kebi compounds have been classified, the Campbell compounds. Lotus is basically a collection of natural products. PFAS compounds is of interest for environmental chemistry. PubChem Light is from Emma Szymanski in Luxembourg. 0PM is also an EU project on harmful compounds. And when clicking on these bullet points here, you can always go to the respective PubChem sets of compounds and download them from the. So for each class, you can basically download all the compounds which belong to this class. You can also search it. So for example, here you have a search for steroids, and then you can see all the concepts which relate to steroids. For example, here you see the 3 oxasteroids of the Kebi compound collection. Okay, so however, when you are able to automatically classify compounds, of course, the next problem arises, that is quality issues. So manual classifications are fine, but I think they are impossible for more than 1,000 structural classes. Then it becomes really boring, especially if you want to re-index everything. So you would have to manually rehearse everything. And also probably impossible for more than 1 million compounds. So this means automated classifications are of course desired, because we can rather discuss classification criteria instead of individual classifications. And they can be improved iteratively and work on many compounds. But then you have, of course, the problem of ensuring quality. We have published this ontology in GitHub and also the automated classification, which works with either Chemaxon software or with CDK Mbit software. And basically, we have thought ourselves, what are quality criteria for the 3 different types of concept formalisms here. One is, of course, calculations. Here, of course, the quality depends on the quality of the software, which I won't discuss further. Concepts defined by smarts combined by and or not logic. Of course, based on the paper we have published in 2012, that goes back to this one paper. And newly we are using ring systems using the ID codes from OpenChemLib for the data warrior logic. Now, in order to ensure the quality, for each leaf concept, we have added smiles with compounds which should be classified as being members of this class. So for example, here we have a concept called polyfluoroalkyl ether carboxylic acids from the PFAS classification tree. And then we have added a SMILES, which automatically should fall into this classification class. And if it's not, of course, then you have to work on the SMARTS definition and improve them. So basically now we can ensure that each SMILES is classified into each class, into its class. So basically every path which leads to a leaf node can be taken, and therefore automatically ensuring that a specific SMARTS definition or set of SMARTS, like here we have two SMARTS which define this class, work. The other concept is ring systems. And here we have a nice tool in OpenChemLib, which is also open access software, Java-based software, cheminformatics software, where you can calculate a ring system, the parent ring system of a compound when you throw it into the program. So for example, for aspirin, we would find that it contains a ring system benzene. So this concept, benzene, contains the ID code, which is shown here, and some characterizations. That's ring size of 6 atoms. It has only one ring. And basically, it also contains SMILES, which should verify that we can reach this node. Yeah, and at the end, you will see an ontology. Basically, you can download these ontologies in OBO and RDF format. And then you can see something like here, where you see that a class like Dalbergi-Chromane derivatives has synonyms, it has SMARTS definitions, it has a comment, and it has example SMILES. And then you see the tree, which leads down to the tree view, leads down to this molecule. Yeah, and basically this is the compound itself, which is basically an instance or a child of this compound class. And here you see where this compound is classified as an aromatic hydroxyl, chiral compound, acetals, dialkyl ethers, and so forth. And it's also containing these ring systems like benzene, which you see here, and then you see the 2H chromines, which is this part of the molecule. So it's correctly classified. Yeah, and basically with that, I would like to finish and just invite you to have a look at this classification browser within PubChem. And of course, we are very open to criticism, improvements, and yeah, ideas. Thank you very much.
Yes, thank you very much from our side.